Welcome to qnawire.
For this problem, we will first write the velocity of Atlas as follows. The velocity of Atlas VA is equal to 2 pi Ra over tau A, where Ra is the radius of its orbit about Saturn, and tau A is its period of that orbit. Now, our data tells us that the radius of the orbit of Atlas above Saturn is 85.54 times 10 to the 3 miles. And this is 451.651 times 10 to the 6 feet. We're also given the period of Atlas's orbit. Tau A is 0.6017 days, and this is 51,987 seconds. So since we have this data, we can then go back to our initial equation and find the speed at which Atlas orbits Saturn, and that's 2 pi into 451.651 times 10 to the 6 meters, or feet actually, over a period of 51,987 seconds. And so we get the velocity of Atlas in its orbit to be 54.587 times 10 to the 3 feet per second. So that is the velocity of Atlas while it orbits Saturn. Now the force, the gravitational force, is given as follows. F is equal to gm times little m over r squared, where big M is the mass of the planet and little m is the mass of the satellite or moon. And because this is centripetal motion of a nearly circular orbit, this is equal to mv squared over r. Remember, little r is the radius of the orbit. And from here we can see that g times m, both are constants, is equal to r v squared. So that's also a constant, rv squared. Now for the satellite, we get the following. The radius of the orbit for the satellite times the speed of its orbit squared must equal to the radius of Atlas's orbit times the speed of Atlas's orbit squared. And therefore, if we rearrange this, we get that the radius of the orbit for the satellite must equal to the radius of Atlas's orbit Ra times Va squared over Vs squared. And again, we are given data. The speed of the satellite's orbit is 54.7 times 10 to the 3 miles per hour. And this translates to 80.227 times 10 to the 3 feet per second. The radius of the satellite's orbit can then be calculated by using the equation above. So Rs is equal to and we substitute our values in here, 451.651 times 10 to the 6 times 54.587 times 10 to the 3 all squared, those values we are shown above, over Vs squared, which is 80.227 times 10 to the 3 all squared. Hence we get the radius of the satellite's orbit, Rs, to be 209.09 times 10 to the 6 feet, which works out to 39,600 miles. So that's the radius of the satellite's orbit, or the distance of the orbit of the satellite above the surface of Saturn. Now, if we want the altitude, we want the radius of Saturn, remember the value we calculated above, little r, is the distance above the center of the planet Saturn at which the satellite is orbiting. So the actual radius of Saturn, capital R, is equal to this value minus the altitude. So the altitude is the height above ground. So this is 39,600 miles minus the altitude of the satellite's orbit, 2,100 miles. Hence we get the radius of Saturn to be 37,500 miles. And next, for part B, we want to calculate the mass of Saturn. So the mass of Saturn, capital M, is equal to Ra VA squared over constant G. So since we have these values, we can calculate this. So this is 451.651 times 10 to the 6, which is the radius of Atlas's orbit, times 54.587 times 10 to the 3 all squared, all over 34.4 times 10 to the minus 9. Hence we get the mass of Saturn in US units to be 39.1 times 10 to the power 24, that's in pound second squared per foot.